And so welcome to TA number 10 of Cognitive Robotics. Today's topic, return of the AI. I mean, the AI never really left, but we'll continue on with it anyways. Today we're going to discuss a different subfield of motion planning. So last week on TA, we introduced the field of motion planning, and that problem, we explained that this problem that we deal with is one in which we have a robot. We have its start location and its end location, a fully observable environment, a set of obstacles in that environment, and we want to move our robot between the start point and the end point without colliding with any obstacles. That's the motion planning problem. And last week we tried to look through some methods for how we would approach this problem. We looked at very basic methods that work really in low dimensions. So let's say we're a point robot. So if we assume that a robot doesn't have width or length, say we have such a robot that can translate only in 2D, so it can go in the X, Y directions. And we assume certain things about the obstacles that exist in space. So we assume that they're all polygons. So for example, if we have just these rectangular tables. And so in those cases, in those really nice, neat cases that are rarely ever true, we have some nice exact methods and some grid-based methods that we could use to solve the motion planning problem relatively efficiently. In the real world, we're going to have robots where dimensionality of the configuration space is going to be much higher than 2 or 3. Once we cross 4, already the methods that we spoke about last week already start to become super inefficient. For example, grid-based search, if you're trying to create a grid in 4D, 5D, and so on, we're exponentially increasing the number of nodes in our search graph. So this is widely problematic. If we want to have any hope of solving motion planning in higher dimensions for 6-DOF robots, 5-DOF robots, and so on, we'll need to be a bit more creative with how we approach solving the motion planning problem. So today, this subfield, this group of algorithms known as sample-based motion planners, this is one of my personal favorite groups of algorithms in general, just due to its pure simplicity and the power of the methods that we're going to explore today. And again, this is based on stuff I've learned in this course taught by Oren Zaltzman, algorithmic robot motion planning taught in the computer science faculty every winter. Highly recommended if last week and this week pique your interest. So as I said, more dimensions, more problems. The higher the dimensionality is of our problem, the more complex our environment is in terms of the shapes of the obstacles, the more DOFs we have in a robot, the more inefficient our exact, our geometric, and our grid-based methods become. They become more inefficient. Now, is all hope lost? No, I wouldn't be here if it was. So moving on, what if I told you that there was a way to tackle this problem with relatively simple algorithms that still don't sacrifice too much in terms of completeness optimality? So this is where these sample-based algorithms come into play. And there's a general, let's say, backbone that guides the concept of these algorithms. What we'll do is we'll sample our configuration space. So we won't assume anything about the configuration space. We won't represent it at all. We'll just sample points we'll sample configurations. So points in the configuration space. So for example, if I have a 2-DOF robot that has 2 revolute joints, maybe I'll sample the 2 angle values. So one of them might be pi, the other one might be pi over 2. So we'll sample such configurations in the C space. We will then look at where those points are in the workspace by using board kinematics, which is relatively efficient. Looking in the workspace, we can check for collisions. We can see if that configuration in the workspace is going to collide with anything. So we can see if I set these values to the joints in my robot, will it crash into anything in the workspace? Then from there, we can start trying to build some sort of graph. So we'll start sampling more and more of such configurations. We'll try and add edges between those configurations in the C space. So we'll be trying to build a graph in the C space. And then we'll look back every so often back into the workspace and we'll see, do these edges, do these configurations, do any of them collide with obstacles? Obviously, if they do, then we'll have to throw those vertices and those edges away. Once we are able to build a graph that's sufficiently resolute for us in the C space, we can then run a pathfinding algorithm like A-star and like Dijkstra on this graph in order to find a path between the start point that we want and the end point that we want for our robot. With these methods, we're no longer going to be able to use the concepts of completeness and optimality as we defined them before. So before we had algorithms like A*, which are optimal, there is no question about its optimality, and there's no question about its completeness. Here, these algorithms will not be complete nor optimal, but they will have a probabilistic sense of those concepts. So instead of being complete, we'll have probabilistic completeness. This means that as I sample more and more and more points, if I sample an infinite number of points, in that sense, my algorithm will be complete. I will always guarantee a solution if I'm sampling an infinite number of points. Likewise, we have asymptotic optimality. This is a similar concept. So as I sample more and more and more points, my solutions will converge to the optimal solution. So I'm getting some sort of idea of how close I am getting to optimal the more and more I sample points. And we'll use these two concepts now to evaluate a few algorithms. So today we're going to discuss two algorithms and one variant. So we'll be discussing the probabilistic roadmap, and we'll discuss the rapidly exploring random trees algorithm, as well as the RRT star algorithm. So let's dive a bit first into the actual steps of general sample-based motion planning algorithms. So the first part, of course, is the sampling. So we have our workspace here on the left, and just computing coordinates X and Y. The robot is just not here right now, it'll be in the next picture. And we'll start by not representing anything in the C-space at all. We won't say anything about the obstacles in the C-space. And this is also one of the best parts of sample-based planners. So we don't need to say anything about the C-space. We don't need to represent it. We'll just take some point according to some scheme. We'll just sample a point in the C-space. So we'll take a point that has two angular values. And then we'll translate that point into the workspace using kinematics. And we see, oh shit, there's a collision. And this is quite problematic. And we'll say, okay, we'll discard this sample because, of course, we don't want our robot to collide because it's expensive and it took forever to set up. This is just a representation of the C-space. Again, we won't be explicitly representing the C-space, but this is just how it would look. So you can already see if we had represented the C-space explicitly, we would see a collision automatically from the sample point. So again, we only want to sample points that are in the free space. So we'll try again, we'll sample another point. This one just happens not to be too far away. And luckily this time we sample the point that's in the free space. So now we see that the arm doesn't collide with anything. And here in the C space, we can see if we had represented it explicitly, there would be no collisions there either. Now, when it comes to sampling, there are a few ways that we can go about actually sampling some space. So we could do it deterministically, we do it randomly, and then there are a few other approaches that rely more on the geometry of the space. So usually the methods that are used most common today are random sampling methods like uniform sampling. So we'll just sample from a uniform distribution between 0 and 1, and whatever points we get, that's our values. Sometimes we don't want to use the random sampling approaches. Maybe, for example, if we need to replicate results. So for example, I think it was Oren told me that NASA used to reject any sampling-based motion planning methods because they didn't want any uncertainty in their Mars rover missions. They would only accept deterministic sampling methods. Today, I think they've eased up a bit. So there do exist deterministic sampling methods. This means that it's a deterministic sequence of, say, points that will sample in space every single time. We can repeat this infinite number of times and we'll get the same result every time. One example is if we create a grid and we just look at the points in our grid. That's an example of a deterministic sampling. We have evenly spaced points all over. And as we already saw last week, it works well enough in 2D and 3D space, but as we get to higher dimensions, it's not so ideal. Other examples are things like Halton sequences. So this is just a clever way to create a deterministic sequence of numbers that looks random. So these points will appear random, but actually they're following a very strict pattern that's replicable every single time. We're not going to discuss this too much, but just I thought it's worth noting that. And the problem that we can reach with deterministic or random sampling is that we're completely ignoring the geometry of our problem. So sometimes we will have the problem that we saw last week with narrow passages. So if you remember from the grid-based search from last week, we saw that if we have narrow passages through obstacles through which our robot will have to pass in order to get from the start to the goal, and we have too high of a resolution, so say we make a grid too big, there's no chance we'll get through this passage. And usually in random methods and deterministic methods, unless we sample a lot of points, it's very unlikely that we're going to get through these little narrow passages. So in the case that we would want to take into consideration the geometry of our C space, of our workspace properly, then we could account for this. There are methods, for example, that try and sample points as far away from obstacles. So this is called medial axis sampling. So here we'll sample points in a certain way, such that they're in between the obstacles always. And you can see that in this narrow passageway, I actually sampled sufficient points to get a path through that little passage. And here, if I just did random uniform sampling, there's no way for me to get through this properly. There's going to be some collision between here and here. So it's going to be never getting through that passage. Rather than going as far from obstacles as possible, we can actually also sample as close to obstacles as possible. So this is called obstacle-based sampling. So here we get as close to all of our obstacles as we can. And this should remind you of visibility graphs from last week. So visibility graphs are a way to get an optimal solution for the motion planning problem in 2D for polygonal obstacles. And in that case, we saw that the optimal path for a robot moving in 2D, that's a point robot moving amongst polygonal obstacles, it will always have to pass through vertices of the obstacles. The obstacles are polygons. It'll always have to touch their vertices, and that'll allow us to create the optimal path between the start and the goal point, regardless of where they are in the workspace. So it's a similar thought here. If we get, again, close to the obstacles, we can create paths that are approximately optimal or closer to optimal than ones like that, which is definitely, you're never going to get optimal solutions from going as far away from the obstacles as possible. So that just covers the sampling methods. Again, we're going to focus mainly on random sampling just because it's the easiest one and it works relatively well. So once we've done our sampling, we've sampled a few points in space, and now we want to know how can we create a graph out of these points. So this is where we run the nearest neighbors algorithm. So in this case, we're going to define some number of points that we want that are close to our original point. So let's say, for example, I have a graph. Let's work today. Black. Oh, goodness. All right, so say we have a bunch of points here. And I want to know what's the best way that I should connect these points in order to create a graph. So we'll use the nearest neighbors algorithm, and we'll decide how many points do we actually want to connect to each of the other points. So, for example, we might decide to use something called the k nearest neighbors algorithm. So we'll choose always some number k of nodes to select for each node. So say, for example, I say k equals 5 or k equals 3. That means that for every node, I'm going to connect it to its 3 closest neighbors. So I see that these 3 are the closest. So I'll add edges there. And similarly for here, 1, 2, 3, and so on. Alternatively, I could, instead of using this k nearest neighbors method, I could use something called r nearest neighbors. So instead of counting a specific number of neighbors, I will build a circle or a sphere or whatever dimensionality object it is. And I'll expand that sphere until I get to a certain radius. So say, for example, I say a radius of 3. So I'll create a circle of radius 3 around this node, for example, here. And any points inside this circle, this radius, I'll take those neighbors. I'll take this one and that one. So there's just 2 different ways to take nearest neighbors. They each have their own benefits and drawbacks. To calculate this, it's actually relatively simple. So we could do the k nearest neighbors, we could do both of them in linear time. This one I think is lower bound in its worst case is linear time. So what do I mean by that? So if I want to know what's the closest neighbors to a point within some radius, all I need to do is look, do a for loop over all of the points that I have, over all endpoints, and just check, is the Euclidean distance between this point and that point less than r? That's it. And calculating Euclidean distance, I can do it for 1. Then I have endpoints, so my O is just n. I mean, I have a linear time to calculate nearest neighbors. For k nearest neighbors, it's a bit different because there's a bit smarter data structures that we can use. we can get this down to log n time. So instead of looking over every single point, we can use data structures like Voronoi diagrams, which is shown here, like KD trees, which I use in my code later on. I think what's the other one? Randomly transformed grids. Yeah. We can use some nice little data structures to get a bit of a faster calculation for our nearest neighbors algorithm. So here I'm just showing the Voronoi diagram because it'll be relevant a bit later. But this kind of diagram, those who haven't seen it, basically if I have a set of points, which I'll call seeds, the Voronoi diagram tells me what region of space is closest to that point. So what I mean is, if I look at any point, for example, within this what we call a cell, every point within this cell is closer to this point, this seed, which is the seed of that cell, than to any other seed. And similarly here, this pink cell, any point I take in this pink cell is going to be closer to that point than to any other point in our diagram. And this is a very useful way to calculate nearest neighbors, specifically in the K1 case. So if I'm looking for one nearest neighbor, I actually need to find out, well, if I have a point in the blue, which cell is the blue? Which seed does that correspond to? That's all I need to do in order to identify what's the nearest neighbor. So that can speed up some calculations in that sense. Then we'll see this again later because it'll be a bit relevant for RRT. But as I wrote here, I'm digressing. So once we've created a graph where we've added all these edges based on whatever nearest neighbors algorithm we're using, we need to check that these edges and the vertices that we sampled in the first place are valid at all. So we've just taken a bunch of points in the C space and a bunch of edges. We don't actually know if we translate them back to the workspace, are they valid?
Valid, like if they collide with anything?
Yeah, valid isn't like they won't collide with anything. So when I'm talking about configurations, just the vertices themselves, I do the direct kinematics back to the workspace. And usually if I have a straight line object, so say for example, I have a robot arm and all my obstacles are polygons, and it's relatively simple to calculate, well, does this arm cross this face of this polygon? That's a rudimentary calculation. The problem becomes complex when we have some robot that has some weird shapes, some like that, and we have obstacles that have some weird shape, and now the geometric nice things that we learned in high school no longer apply here. So what we can do to reconcile that and check, well, will these obstacles collide, is we can use something called bounding volumes. So bounding volumes is a simple concept. If I have some weird geometry, some weird geometric object, I can just surround it by some rectangle, for example, it could be a sphere, doesn't matter. Some rectangular prism larger than it. And this will be an overestimation of the volume of that object. So here I have a rabbit, and I'm going to overestimate volume using a rectangular prism. And the reason I do this is because if I'm looking in a workspace and I see that this rectangular prism does not collide, if the rectangular prism does not collide, yes. If the rectangular prism doesn't collide with any obstacles in the certain configuration, then I know that for sure, because I'm overestimating the volume of my object, I know for sure that the object inside the volume will not collide with anything either. So if I have this thing inside is some weird shape, if I know that it avoids all the obstacles, that the bounding volume avoids all the obstacles, then for sure the object inside avoids them. And that's one way to do collision checking. And that's when we're looking at just a configuration. So that's when we have a robot stationary at one point. But what happens when we want to look at these paths? So we have these edges in our configuration space, and that's responding to the robot doing some movement. So it's picking up its arm and it's moving somewhere. And the problem with that is that that's a continuous movement. So I can't just calculate the configuration, the bounding volume, for example, the whole time, because that's a continuous action. So I'd have to do that an infinite number of times. So there are ways to get around that. There is an exact method called swept volume, I think. There's an exact method called swept volume that solves this problem exactly, but it's quite computationally expensive. One way we can go around that is we'll just discretize and we'll just calculate the configurations at a certain number of points. So we'll just check, okay, at so-and-so points along this path, do we collide with anything? If we don't collide with anything along this path, along 7 points, then we'll just assume that we're always okay. And obviously the higher the resolution, the better the approximation of whether or not you're colliding with an obstacle. So that's that. Are there any questions so far? Anything unclear? Okay. So once I have my graph where I know that every edge is collision free and every vertex is collision free, that means I've built a roadmap in my free space that connects my start node and my goal node. And I can now find a path across that roadmap that should be valid for solving the motion planning problem. So again, we'll do pathfinding. As we've already seen A star before, and we've mentioned Dijkstra briefly last week. There is code for it. But for those who aren't familiar with Dijkstra is kind of similar to UCS. So instead of using heuristics like how A star does combined with cost, Dijkstra just looks at cost. So it's gonna expand nodes based on whichever ones are the most cost efficient according to whatever cost function is decided. The general Dijkstra algorithm, it has a start but no goal, so it'll check the fastest path for every node from the start for every single node in the graph. So that means that we can know, for example, say we have a multi-query problem, say we have a roadmap and we want to examine it multiple times, we want to solve a motion planning problem for all different goals points. We can actually just solve the whole graph and find the shortest path to start all points in the graph. And that way, whatever our goal node is, we always can easily just reference this graph and find the shortest path. And we've saved some comp power. In this case, we're just going to focus on Dijkstra where we do have a goal point. And in that case, it acts quite similar to UCS. If you remember uniform cost search, again, it's just expanding cost contours. So it's just moving through nodes with according to their cost values. So that we will get to the goal node and we'll know that that's the lowest cost path. So it's optimal in the sense of cost. So that's it. Once we run our pathfinding algorithm, we have a solution. We're done. We've got our motion planning solution. We can do some nice things to that solution. We can use shortcutting, so we can connect points. Say, for example, I have a solution that goes like this, but there's no actual obstacle here. I can use something called shortcutting. So instead of going this whole way, I'll just check to see if this pair of vertices have a straight line path between them. And this is one way, for example, to kind of optimize their paths. If you want to do that, we can also try and smooth our paths. So if we have a real robot, or we are trying to find a more optimal version of a path we have that's just straight lines, then obviously the more optimal version will be some curve through it. And we can try and take that curve instead of those straight lines. So let's look at some actual algorithms now. So the first one we'll look at is probabilistic roadmap, which is it's very much what we've just described. It's almost one-to-one with the recipe we've explained here. It was developed in 1996 by Lydia Kabraki, who's very well known in the field of motion planning for her contributions. It's the first motion planner to give efficient solutions in dimensions higher than 5, which is a very, very big deal. You have 6-stop robots, for example. And it also is a multi-query motion planning algorithm, which means that once I have the roadmap that it's going to build, I can use it multiple times. I can ask it for multiple configurations of certain goal points, and we can easily calculate the best path multiple times between any start and goal point that we want. So I'll explain it through an example. So say I have this 2D C space or workspace. I'll just say it's a point robot so that they're equivalent. And I'm going to go from start to the goal, and here my obstacles are not polygonal, so I can't use any of our exact methods. And I'm not going to bother with the grid-based method. So first I'll sample endpoints in the C space. You already see that there are some collisions with those symbols and the obstacles. I'll run my collision checking in the workspace. So I'll use for kinematics to go to the workspace. Here I don't need to because the workspace and the C space are identical. Well, let's say I did. So now I'm looking in the C space. I do collision checking. So I use geometry in this case because they're just points and circles. I see that these points are in these circles, but round objects. I see that these points are in these round objects, and I just throw them away because I know that those configurations are not valid for a robot. Next, I use some nearest neighbors algorithm. So here it's an RNN algorithm. I built some radius on each point, and I check and I add an edge to that point and all of its neighbors that are within that circle. So I do that, and again, there are some edges that will cause obstacles up here, and we need to remove those edges because that's obviously going to cause a robot to crash. So we use some local planner to do that collision checking. So in this case, for example, we might discretize this line and check a bunch of points on this line. Well, does a point on this line collide with an obstacle? In this case, we'll very quickly see yes. We won't have to do too many calculations, and we'll know quickly that there is indeed a collision there. Then we can remove all those edges that are invalid, and voila, we're left with our roadmap, which contains nodes, vertices, and edges that are only contained within the free space. So none of them are collisional. And of course, then in this case, we have the start and the goal points already in the roadmap, but in general, if I didn't have them, I could add any start and goal points to the roadmap, and I would still have this nice graph over here that I can use multiple times. So that's what we mean by multi-query. Just use the same graph over and over again for the same space. In this case, I run something like Dijkstra, and I will get the shortest path on this graph, not in regular space. I'll get the shortest path on this graph from the start to the goal point. So already you can see that this algorithm is not optimal in the sense of, in the classical sense. We see that this path is nothing of the shortest we can achieve. Is it complete? In the classical sense, do you guys think that it's complete? You're shaking your head. Why?
Because if you sample points that are too far for your radius, you might never find a way to connect them to the end goal or.
Yeah, that's a great point. If you choose your R incorrectly or you choose your K incorrectly, you might end up just not connecting enough edges, and your graph will be incomplete and have no solutions. So PRM is not complete or optimal in the classical sense, but luckily in the probabilistic sense, it's actually both probabilistically complete and asymptotically optimal. So if I add infinite points into my sample infinite points in my free space, you can imagine that I'll have the densest graph possible. And on the densest graph possible, I will of course have every single possible path in the free space. And if I have every single possible path in the free space, then of course I'll get the optimal one. And so PRM will be asymptotically optimal and probabilistically complete. So there's a bit of code that I've added here. This is from my final project for this course from last year. Kind of taken a little modified version of it. Basically, what we did in our project was we did some task and motion planning for a Mars rover, a very simplified Mars rover problem. Sorry, and we used PRM in order to calculate paths for a rover moving throughout some Mars environment. So in this case, we have our initial C space. We have the rover will get this blue point. We wanted to get this green point, and we wanted to avoid all these circular obstacles, all these orange circular obstacles. So let me run that code so you can see what it's going to do. So I couldn't get it to run inside the script, so we'll just have to run it from a terminal. Should find this. So here you will need the SciPy library to run this, just because it uses KD trees, which we didn't really discuss, but it's a data structure, like a K dimension tree, sorry. K decision tree. I'll figure that out later, what D stands for. But the point is it uses an efficient data structure in order to find nearest neighbors. So here, again, I had it randomly generating the start, the goal points, and the obstacles, so these will look the same. So let's say this is my initial map. Fix it out. Now it's going to start sampling. So here it's doing this sampling process, adding all these black points. It automatically does collision checking, so otherwise I'm not adding any points inside the obstacles. And now it's using K nearest neighbors, set to 5, if I'm not mistaken. And so it's adding now a bunch of edges, and again, it's doing collision checking behind the scenes. So now it's not going to touch across any obstacles, and we'll have built a probabilistic roadmap
I have some question. When you said you put the first algorithm to solve for 5 dimensions, do you refer to dimensions of the speed thing?
Yes. Yeah, the dimensions of the workspace and the C space don't always have to line up. So even if I'm in Cartesian 3D space and I have a 6-stop robot, imagine the C space of the 6-stop robot is 6-dimensional, not 3-dimensional. So yeah, it was the C space.
So in that case, you have to find when you start in your end, like a line that connects in 6 dimension space.
Like imagine you have a 6-stop robot and it needs to change all its angle joints like continuously.
Right, they have 6 dimensions.
Yeah.
So you can like connect the line in 6-dimensional space.
Yeah. I mean, there's no way. I mean, we can't visualize that.
Yeah,
Like the algorithm like deals with that relatively fine, like relatively efficient compared to other methods. I mean, like at the end of the day, what you're doing is you're just sampling like how many times there are dimensions. So for example, here I have 2 dimensions, so I just sample once in the y direction and once in the x direction. So if I have 6 dimensions for my C space, I'll just sample 6 times for each point, rather than 2 times for these 2D points. And the algorithm doesn't really care between them. Like, it'll just be a bit less efficient. So now we'll get to another really interesting algorithm. So this one's a bit different than PRM. It's called rapidly exploring random trees. The idea here is that instead of building a graph, we will build a tree. This will be much faster than building a graph. And it'll actually make our lives much easier because if we build a tree in the way that I'm explaining here, we won't need to do pathfinding. We'll automatically be able to just use recursion to get from the goal to the start node without having to run Dijkstra or A-star or anything. The drawback here is that this is a single query motion pattern. So if I have a start to goal node, then that's it. Like I can only use the graph the tree that I get for this algorithm for that start point and that goal point. I can't reuse this. So there's a trade-off between everything. So this one was introduced in 1998 by Stephen Laval, another preeminent motion planning researcher. It's one of, if not the most commonly used motion planning algorithm today, just because it's so powerful in higher dimensions, 5, 6, and so on. I'll give you a little spoiler. It is probabilistically complete, but it is not asymptotically optimal. And we'll see what we can do with that later on with a different algorithm called RRT star to reconcile that fact and somehow get an optimal, probabilistically optimal motion planning. So here I'll draw this one on the board because it's here in the middle. Well, let's say that I have my I have my start point, which is over here. I have my different color. My goal point over here. So what I'm going to do with this algorithm is I'm going to try and cleverly build a graph, tree, sorry, that goes from the red point to the blue point. So what I'm going to do is I'm going to sample a point in space. Again, sorry, this is in the C space. I'm going to look at, again, all the motion planning algorithms we discussed here are looking through the C space, because that's in the language of the robot. So I have the start point, I have the goal point. What I'll do is I'll sample a point. So I sample it here. Let's ignore the goal point for now. Imagine that it doesn't exist. What I started by doing is I add the start node to the tree. This will be the root node of the tree, so it's the top of whatever tree I'm looking at. I sample a point in space, and now I'm going to look what's the nearest neighbor of this point. So the nearest neighbor of this point is the start node, and I'm going to want to draw an edge between the sample and the start node. I'll check that this is collision free. Let's assume that this edge is collision free. And now I've started building my tree. Again, I'll sample another point and I'll check what's the nearest neighbor. In this case, it'll be this point. If this is collision free, I'll add this edge. I'll sample another point. Now let's say that this one, this is the nearest neighbor, but it's not collision free. So I'll just throw this away and I'll just throw away the point as well. And what this is going to allow us to do is going to allow us to start building some tree in space and start connecting points all the way around. Let's say. I'm randomly sampling, and eventually, back to blue. Eventually, through a trick that I'll explain in a second, we'll hit this goal point. And now you see, because it's a tree, there's one path that goes from the start to the goal. So I just use recursion once I reach here. I just look back through the parent nodes and every single node, and boom, I've solved my motion planning problem in linear time for these vertices without any needs for any pathfinding algorithms. No A star, no Dijkstra, nothing. This is part of why it's called rapidly exploring random trees, because one, it can sample and build the tree so fast, and two, because we can go back to that tree so quickly.
The way you describe it, you can just always make the lines that doesn't have any like splits. That's aesthetic. Like it'll just go one and keep going with that.
I know, no, it doesn't go with the same point. It always goes to the nearest neighbor. So say, for example, right now I sample a point here. The nearest neighbor is this one, so it'll build here. If I would somehow sample here, I would just keep building that and so on. But like I'm sampling through the whole space uniformly, so it'll then go wherever. So one thought you might have is that, well, I will never have hope of a uniform sampler sampling my goal point. It is literally impossible, probabilistically, that without me telling it otherwise, the probability would be 0 for me to sample this point. So what do I do? So, no, not that. You could do the closest to, you could create a goal zone, but still, I mean, if you're trying to be as close to the goal as possible, it's not always what you want. So what we could do is we can tell our tree, sample 5% of the time, choose the goal node. Just use the goal node. 95% of the time, choose a random point. But this is called goal biasing, and what it means is that we have an actual chance of adding the goal to our tree for any given moment. So I sample 95% of the time, I add a bunch of random points, and 5% of the time, I'll be looking at the goal node. And if there's a collisionless path to the goal node, I can add it to the tree, and voila, I've created my tree. And of course, the root node is the start node, so I have no problems with my start node. And I can just use recursion from here, look at the parents, and all the way back to start node. And no problems there. With the goal biasing, the higher I make my goal biasing, so if I raise it from 5% to 20%, for example, it's kind of like an incentive for my tree to look for the goal more and more often. So it'll kind of make a pattern towards the tree, but of course you don't want to make this too high. So there's always, as you can imagine, there's a trade-off, but there's some balance. The generally accepted value to use is 5%. So we'll usually sample the goal node 5% of the time, but you can try any values you want. In the code that I have later, you can change that value yourself and see how it reacts.
Is it again like when it adds a node, is it really random or does it have a radius apart from the last one that it added? You know?
Okay, this is actually a great segue into my next point. So it's a uniform random sampling. There is no information granted for the next point when I sample. The reason this tree can explore so quickly is due to Voronoi diagrams. So if I look here, back at this thing. Imagine that the edges of this Varna diagram are my tree, if you will. So I have these big pieces of space here that correspond to the Varna diagram. Let me ask you in general. So say I have this space. What is my probability of sampling here? 1/4, and 1/4, 1/4, 1/4. The probability of sampling a point uniformly out of some area is proportional to that area you want to sample in out of the total area. So Varna diagrams kind of explain to us why this works so well. In that if we have these big regions of empty space here, like we see over here, we're much more likely to sample from those points just probabilistically. We're more likely to sample points just because they have larger area. So as this tree grows and grows, and if I start putting points here and here, well, this region gets smaller. This region still has a larger area, and I, statistically speaking, am more likely to sample here. And this actually contributes to the fact that the trees are called rapidly exploring because they'll just happen to explore free space quickly, but just purely off statistics. So boom, they'll put a point there just because it hasn't put a point there in a while, and uniform sampling and so on. So we'll get that and that and so on. So thank you for the segue there. It was really helpful. So on, and again, this tree is, if you would imagine building the boundaries of the Varna diagram so it can help you understand. Well, it's going to start sampling here and here and here and here and here, and all of a sudden we have a dense graph that's explored a lot of the free space. So that's the RRT algorithm. It's like PRM, it's straightforward. Nothing's too complicated. There are ways to kind of improve it. So first, I'll show you how it looks over time. So it's kind of hard to see because it's small right now. It's running some iterations. So here we see the trees growing through free space. So again, if you imagine that this is the Varna diagram, you have these regions of space, and it's sampling all the time these points of space. Now, there's a reason why you're not seeing points all of a sudden pop up here and branches pop up here, and that's because they're using a method called extend. So rather than do it this way, where every time I sample a point and I have a nearest neighbor, I'll add the line directly between them. What we can do is we can use a little trick called extend, where instead of going this whole way between this point and that point, I'll only extend it up to some value. This is step size eta. I'll only extend up to that point, and then that's where I'll add my new point. I'm not going to go all the way here. So for example, say I have some new point. I'll call it x rand. Its nearest neighbor is here, it's x near. And rather than connect all the way here, if this is collision free, I'll just extend it a bit. I'll stop at some point according to however I define my step size beta. And I'll actually add x new, this point and not this point, to my graph. And what this does is it makes the expansion of the tree a bit more concise. You can see how it's behaving here. It's building its branches in a, I guess, you call it a more efficient way. So you see, that's why it's not exploring. You think it's not exploring its free space, but it assuredly is. It's adding all the time in this direction and that direction. And here, if you watch where it's expanding, it's always expanding in these big directions because it's just sampling the most points out of these regions that haven't been explored. And so you kind of build some sort of an intelligent tree. And again, with the goal biasing, we don't have to worry that we'll miss the goal. We know that at some point we'll add the goal. And for the goal, in that case, you might say, well, if I run into the zero paradox, or if I try and take some fraction of this distance every single time, I'll just get closer and closer and closer and never get there. So one way to get around this is instead of making this eta a fraction of the distance, you make it a constant value, and then like you're guaranteed to cross through. And if you cross through, then you'll take this point and put it off. So that's one way, and I guess the other way would be that if you ever sample a goal point, just don't extend, just go all the way through. Either way, if you do either way, you can see that it'll have more or less minimal difference between them. The first way is preferable. So usually you would just extend to the goal point because if you're early on in your tree and you sample a goal, you don't want to draw lines going all the way here. You'd rather just sample like here. This depends on what you want to implement. So like I said before, this is probabilistically complete, but it's not asymptotically optimal. So in the way I've defined it, we stop once we reach the goal. So you can already see that it's not optimal, and it doesn't matter how many points I sample. If I'm gonna stop as soon as I hit the goal, I have no hope of making this optimal. And you could also run this algorithm where instead of stopping immediately at the goal, you should just keep sampling points. However, in the way I've defined it, it's not gonna update the cost of this path. Nothing's gonna change here, and so this still won't be optimal. So RT in this sense, it's not gonna be asymptotically optimal. It doesn't matter how many points you sample, but it's still relatively fast algorithm. The runtime, I think it's ON log. Let's check. Yeah, ON log n. So it's also quite a fast algorithm. Does it search all the way through quite nicely. And it always builds nice pretty pictures. This is just a visual explanation of the extend. So if anybody who didn't understand what I was talking about, that's what it looks like in a graph. So I'm running out of time, but I'll very quickly try and explain RT star. RT star is kind of a way to get around this problem of the not asymptotically optimal RT, just by a very simple change. So what I'll do is I have my RT, I'll look at this point x round. So of course the nearest neighbor of x round is over here. And regular RT will just try and extend from here, from x nearest to x round. The thing is though, is that the path between I showed it here. Yeah, the path from x in it. If I would use, yeah, if I look at a different node that exists in my RRT tree and I connect that other node to this new point, it'll create a shorter path than I would if I achieved going through the whole way. So what we care about is the fact that we're kind of losing costs, we're making worse paths because we're taking longer paths, mainly because we consider only nearest neighbors and not almost nearest neighbors. If I consider this point instead, I'm testing it here, despite the fact that there's an obstacle, that would give me a shorter path, and overall my tree would be getting shorter and shorter if I did that. So what I'll do is I'll consider the other nearest neighbors. So I'll again use a KNN algorithm or an RNN algorithm. I'll consider a set of nearest neighbors. I'll look at the nearest neighbors. I'll see, is there a collision-free path? In this case, there isn't. But then I'll consider this one. And you can see already geometrically things are Pythagoras. This path should be shorter than this path. And so if I consider this nearest neighbor instead of this nearest neighbor, then I would get a faster path from x in to x chunk. So what I'll do is I'll rewire the tree. I'll change this edge that I just added, this original edge that I had between x prime and x child. I'll change it to come from x potential transfer instead. And I'm left with the new RT that has a shorter path from x in to this point than what there was before. If we apply this rewiring step every single time that we add a new sample, what we'll eventually get is an asymptotically optimal algorithm. Let me see if I can show it to you how it looks here. So this is the code that also comes with this TA. Just run it. So again, this should be familiar to you from last week. I use this for the grid-based search. So again, we want to plan the path from the red point to the green point. So this is going to be my regular RT, not the RT star. And if I run RT, again, you see I'm using the extension. So I'm getting these little changes, not huge changes in the trees, in the branches. And again, I easily find the path by reaching the goal point and recursive that to the start point. And you guys should notice immediately once I do the RRT star planner, you'll notice the interesting difference between them. As you see, this is a much more, I guess, focused tree. We've rewired the tree, and so these paths from the start to ending point are much more optimal, especially as the tree gets deeper and deeper. So I've now found a much more cost-effective path from the red to the green. If I compare it to here, we see I go all the way to this edge for whatever reason, just because I'm not considering the fact that I have other nearest neighbors that might be actually more cost efficient. So that versus that. And you can see you can identify how the neighbor looks. It looks more like a Christmas tree, if you will, than a bush, like the other one. So that's it for today. We've finished the topic of motion planning. Next week, we're going to discuss the merger between task planning and motion planning. So if I want to teach my robots to do my dishes, it needs to know what order to do those dishes, but it also should know what servo values does it need in order to move those dishes. So we'll discuss that next week. Anybody who wants to stay now to discuss homework 2, feel free to do so. Thank you guys very much. See you next week.